Areas between curves. We begin here with a summary of some important ideas concerning area calculations in the familiar case of a region bounded by the graph of a non-negative function and the x-axis over the interval AB, that is, the area under a curve as illustrated here. Recall that we can approximate the region with adjacent rectangles whose top edges touch the curve. A typical rectangle has height equal to f of xi hat, where xi hat is some number along the rectangle's bottom edge and width delta x. And so its area is f of xi hat times delta x, which we can denote by delta a sub I, indicating a small piece of the total area. Summing all such areas provides an approximation to the total area A. Such a sum is called a Riemann sum, and the exact area is the limit of Riemann sums as delta x goes to 0. This is the integral of f over the interval AB. The following analogous notation and terminology is convenient when computing areas by integration. Rather than thinking of a typical rectangle with finite width, we think of the area differential dA equals f of x times dx as the area of a thin slice with height f of x and width dx. The definite integral that gives the area A is the integral of the differential dA from x equals a to x equals b, that is, the integral from a to b of f of x dx. Now let's consider a region that's bounded below by the graph of y equals g of x and above by the graph of y equals f of x between x equals a and x equals b. Note that if g of x equals 0, this is the same as the previous case. Just as before, we can approximate the region with rectangles. Here, the bottom of each rectangle touches the lower curve. The area of a typical rectangle is therefore delta a sub I equal to f of xi hat minus g of xi hat delta x. Note that the height is the difference between the two function values at xi hat. Summing all such areas provides an approximation to the total area A. Again, we think of the area differential dA equal to f of x minus g of x times dx as the area of a typical thin slice. And, just as before, the area of the region is the integral of dA from x equals a to x equals b, only now the formula for dA is slightly different, or rather, slightly more general. A crucial thing to remember here is that the integrand is the function whose graph is the top curve minus the function whose graph is the bottom curve. Thus, we're always integrating a non-negative function. Example. Find the area of the region bounded by the graphs of y equals sine x and y equals cosine x between x equals pi over 4 and x equals 5 pi over 4. Here's a graph of the two curves which intersect at x equals pi over 4 and x equals 5 pi over 4. So the region of interest is the one shaded in yellow here. A rectangle approximation of the region looks like this. The top of a typical rectangle touches the graph of sine x, and its bottom touches the graph of cosine x. So its area, delta a sub I, is equal to sine of xi hat minus cosine of xi hat, all times delta x. The area differential, dA, equals sine x minus cosine x dx. So the total area A is the integral from pi over 4 to 5 pi over 4 of dA, sine x minus cosine x dx. Now let's do the computation. Sine x is the derivative of minus cosine x, and minus cosine x is the derivative of minus sine x. So an antiderivative of sine x minus cosine x is minus cosine x minus sine x. We want to evaluate that between pi over 4 and 5 pi over 4. Now 5 pi over 4 is a third quadrant angle, so we get negative values for both sine and cosine at 5 pi over 4, Those values are both negative root 2 over 2. So the value of minus cosine x minus sine x is plus root 2 over 2 plus root 2 over 2. Then we subtract the value at pi over 4. At pi over 4, both sine and cosine are root 2 over 2. So we're subtracting minus root 2 over 2 minus root 2 over 2. The first of these equals root 2, and the second of these equals minus root 2. And so we have root 2 minus minus root 2, or 2 times root 2. This is the exact area of the yellow region. Now let's look at another example. Find the area of the region bounded by the graphs of y equals x squared and y equals x plus 2. Here's a picture showing the two graphs and the region whose area we'd like to compute. The first thing we want to do is find the x-coordinates of the points of intersection of the two graphs. Those will end up being our limits of integration. So what we'll do is we'll set the two functions equal to each other and solve for x. We rearrange the equation and factor, and we find that the two roots of the equation are x equals minus 1 and x equals 2. Now let's look at a typical vertical slice in the region. The top of that slice is along the straight line y equals x plus 2, and the bottom of the slice is along the parabola y equals x squared. So the length of that slice is x plus 2 minus x squared. So we'll write our area differential dA as x plus 2 minus x squared times dx. And so the area is the integral from x equals minus 1 to x equals 2 of dA. Now we'll antidifferentiate each term. We get 1/2 x squared plus 2x minus 1/3 x cubed, and we evaluate that between minus 1 and 2. The value at 2 is 2 plus 4 minus 8/3. The value at minus 1 is 1/2 minus 2 plus 1/3. Now let's do this arithmetic by first gathering together all the whole numbers. We have 2 plus 4 and then a minus minus 2 for an 8. Then we have minus 8/3 minus another 1/3, which is minus 9/3, and then we have a minus 1/2. Of course, this is 8 minus 3 minus a half, or 5 minus a half, which is 9/2. Example. Find the area of the region bounded by the graphs of y equals 2 times the square root of x, y equals 0, and y equals 3 times the square root of x minus 5. Here's the graph of y equals 2 times the square root of x. The graph of y equals 3 times the square root of x minus 5 touches the x-axis at x equal to 5 and looks like that. The graph of y equals 0 is the x-axis, so the region that we're interested in is shaded here in yellow. The first thing we'll do is find the point of intersection, which will help in determining our limits of integration. To do that, we'll set 2 times the square root of x equal to 3 times the square root of x minus 5. Next, we square both sides of that equation, and then by subtracting 4x from both sides and adding 45 to both sides, we arrive at 45 equals 5x. And so x equals 9 at our point of intersection. For the y-coordinate there, we could go back to either of the two functions. The simpler of the two is 2 times the square root of x, so we have 2 times the square root of 9, or 6, for the y-coordinate. Now let's look at vertical slices here. Toward the left side of the region, a vertical slice touches the graph of y equals 2 times the square root of x and y equals 0. But if we move to the right, the slice then touches y equals square root of x and y equals 3 times the square root of x minus 5. So if we follow this approach, we're going to have to break the region up into two pieces, because the length of the slices will need to be described differently in different parts of the region. The cutoff point here is at x equals 5, clearly. And so to get the area of the left part of the region, we'll integrate from 0 to 5, 2 minus the square root of x minus 0. And to get the area of the right part of the region, we'll integrate from 5 to 9, the y-coordinate on the top curve, which is 2 times the square root of x, minus the y-coordinate on the bottom curve, which is 3 times the square root of x minus 5. Now these are not difficult integrals to do, but there's a simpler approach here that will allow us to capture the entire area with one integral. To The key here is to look at a horizontal slice located at a height of y. This is because the length of that slice can be given by a formula that's independent of where it is in the region. In other words, all horizontal slices are basically the same. The length of the slice is going to be given by the x-coordinate on the right end minus the x-coordinate on the left end, but these have to be described in terms of y. So we need to solve for x in each of those two equations involving square roots. For the curve on the right, we'll divide by 3 and square both sides, and then add 5 to obtain x equals 1/9 y squared plus 5. For the y equals 2 times the square root of x curve, we'll square both sides and divide by 4, and write that as x equals 1/4 y squared. So our slice area is going to be given by the x-coordinate on the right, 1/9 y squared plus 5, minus 1/4 y squared, and then times dy. Now let's simplify that a bit. 1/9 minus 1/4 ends up being 5/36. Let's also go ahead and factor out 5/36 so that we have 5/36 times 36 minus y squared dy. Now y coordinates in our region extend from y equals 0 to y equals 6, so that's the interval over which we want to integrate dA. So the area is the integral from 0 to 6 of 5/36 of 36 minus y squared dy. This is a fairly simple calculation now. Our antiderivative for 36 minus y squared is 36y minus 1/3 y cubed. And we evaluate that between 0 and 6, which is 536 times 216 minus 1/3 of 216. So we have 536 times 2/3 of 216, which is 144, and 144 divided by 36 is equal to 4, so our area ends up being exactly 20 square units. Example: find the area of the region bounded by the graphs of y equals x squared and y equals x to the fifth two ways. By that we mean by integrating with respect to x and by integrating with respect to y. Here's the parabola y equals x squared, and here's the graph of y equals x to the fifth. Notice the points of intersection are obviously the origin as well as the point 1, 1, and here's our region. Now let's zoom in on that a little bit. Let's first look at vertical slices. This corresponds to integration with respect to x. Here's a vertical slice located at an arbitrary x. The top of that slice is on the curve y equals x squared. The bottom is on the curve y equals x to the fifth. So the length or the height of that slice is going to be x squared minus x to the fifth. And so our dA is x squared minus x to the fifth times dx. So the area is the integral from 0 to 1 of that dA. The computation here is easy. The antiderivative we want is 1/3 x cubed minus 1/6 x to the sixth. And evaluating that between 0 and 1 gives us 1/3 minus 1/6, or 1/6. Now let's do the computation from the point of view of horizontal slices. That will correspond to integration with respect to y. So suppose we have a horizontal slice located at y. Its length is going to be the x-coordinate on the right minus the x-coordinate on the left, but those have to be described in terms of y, so we solve y equals x to the fifth for x, getting x equals the fifth root of y, and solve y equals x squared for x, getting x equals the square root of y. So dA here is going to be y to the 1/5 power minus y to the 1/2 power times dy, and the area is the integral from 0 to 1. Notice that's y equals 0 to y equals 1 of y to the 1/5 minus y to the 1/2 times dy. Now again, this is a straightforward calculation. Your antiderivative here is 5/6 y to the 6/5 minus 2/3 y to the 3/2. And we evaluate between 0 and 1, obtaining 5/6 minus 2/3, which is equal to 1/6. One more example. Let's find the area of the region bounded by the graphs of y equals 3 times 1 minus x squared and y equals 4 times the square of 1 minus x squared. Now let's get a picture of what we're dealing with here. Here's the parabola y equals 3 times 1 minus x squared. Notice the x-intercepts are plus and minus 1, and the maximum value of 3 occurs at x equals 0. In the other equation, y is equal to a fourth degree polynomial in x with zeros at plus and minus 1 and a value of 4 at x equals 0. It turns out that the graph looks like this, and so the region bounded by the two graphs looks like so. Now notice that there are 4 points of intersection, 2 of which are obviously located at plus and minus 1. The other 2 are indicated here, and to find those, let's set our two functions equal to each other and solve. Since we're looking for solutions other than plus and minus 1, we may as well divide through by 1 minus x squared here to obtain 3 equals 4 times 1 minus x squared. Now we multiply out the right side, do some rearranging, and we have 4 times x squared equals 1. So x ends up being plus and minus a half at each of those points of intersection. Now notice that we have symmetry here about the y-axis, which tells us that we may as well just compute half the area and then multiply by 2 later. Now since the curves cross at x equals 1/2, we're going to need to break the calculation up into 2 parts. We'll calculate one integral from 0 to 1/2, and then another integral from 1/2 to 1. Between 0 and 1/2, the top edge of the region is the fourth degree curve, and the bottom edge of the region is our downward opening parabola. So the length of a vertical slice there is given by 4 times the square of 1 minus x squared minus 3 times 1 minus x squared. Between 1/2 and 1, it's just the opposite. So we'll integrate from 1/2 to 1, the opposite difference. Now let's work out these integrals. We'll first simplify the integrands. Notice that each one is just the negative of the other. Now when we multiply out 1 minus x squared squared, we pick up an x to the fourth term, so we have a 4 times x to the fourth, and we also get a minus 2x squared, which gets multiplied by 4 for a minus 8x squared, and then we have a plus 3x squared from the other term, so we have minus 5x squared, and the constant term ends up being 4 times 1 minus 3 times 1 for a 1. So we'll integrate from 0 to 1/2, 4x to the fourth minus 5x squared plus 1, and then integrate from 1/2 to 1, the negative of that function. Now let's antidifferentiate and evaluate between the endpoints. Our antiderivative is 4/5 x to the fifth minus 5/3 x cubed plus x, and for the second term, we just have the negative of that same antiderivative evaluated between 1/2 and 1. Now we substitute 1/2 into the first term and subtract its value at 0, which is 0. Then we add the value of the second antiderivative at 1 minus its value at 1/2. And so now let's do all this arithmetic. Notice that we have 4/5 times 1/32 plus another 4/5 of 1/32 for an 8 over 160. We have minus 5/3 times 1/8 minus another 5/3 times 1/8. So we have minus 2 times 5 over 24, or minus 10 over 24. We also have plus 1/2, minus 1, minus a minus 1/2, all summing up to 0. Now the only terms we haven't accounted for are minus 4/5 and 5/3. Now let's reduce the first two fractions. Our common denominator is now going to be 60. And finally, we finish this off. We have 30 over 60, or exactly 1/2. Now remember, that's just 1/2 of the area, so we'll multiply by 2 to get an area of exactly 1.